Okay, good morning. So yesterday we were looking at some of the applications of CNNs. So we saw one which where you classify static images, one where you classify videos to identify actions. So in fact, now this time we will look at a even older application. So one of the first one which made CNNs very popular and has showed that you can really classify large data sets. Right. This is called AlexNet, popularly called AlexNet. But basically, this is a group where they have taken large data set called ImageNet and classified using a large CNN architecture. So the goal of this CNN study is to classify 1.2 million hyper-resolution images into 1,000 different classes. The source of this data is a much larger data set called ImageNet, which had 15 million images and classified into 22,000 categories. So this was manually labeled by a large number of people using this Amazon mechanical turk scheme. So for this, they have taken architecture which looks something like this. I'll show you a simpler picture later. So they have taken this 1.5 million, 1.2 million images and classified into 1,000 classes. So they use ReLU nonlinearity and they found it is much faster than using tanh and other sigmoid functions. And they use dropout layers to improve generalization and use stochastic gradient descent and also introduce methods like momentum and weight decay. Weight decay is for improving generalization and like I think discussed before, momentum is for improving training speed. So it took about 5 to 6 days to train this on multiple GPUs. So just to give an idea of how large this network is. So the image size is 227 by 227. So in 3 colors, you have 3 images, RGB. And the first layer, let me. So you know that from the image, there is an image, and if you go to the first hidden layer, every neuron is connected to only a window of pixels in the input image. So this is called a kernel. And so you have 3 images like this, right? So you will have 3 such kernels going from each neuron. So the kernel size is 11 by 11, and there are 3 of them. And the first hidden layer had 96 feature maps. Each of them was of size 55. There are totally, in the first hidden layer, there are totally 55 by 96 neurons, that is 290,000 neurons. And each of them has a kernel of size 11 by 11 by 3 and one bias term. So the very first hidden layer itself has so many weight parameters. 290,000 times 364, that is 105 million weight parameters. That gives an idea of how large this network is. So they use ReLU transfer function or the activation function because it's a piecewise linear and computationally lot less expensive. And they found that ReLU used for this dataset called CFAR10 dataset, another image dataset. Right, the same network, if you just replace the sigmoids with ReLUs, it trained 6 times faster. Yeah, so actually 1 second. Yeah, so this network, this picture gives a better depiction of the architecture. So input is, like I said, 227 by 227 and 3 planes of this. And the next layer, so basically it has 5 convolution layers followed by 3 fully connected layers. The 5 convolution layers are like this. So convolution and max polling, convolution, max polling, convolution, max polling, and so on, 5 of them. So followed by 3 fully connected stages. So you see that again the standard pattern is seen. So here when you go from first convolution to the max polling, your feature map size shrinks from 55 by 55 to 27 by 27. The number of feature maps is the same. Now from this stage to the next convolution stage, the feature map size has not gone up, but the number of feature maps has gone up to 256. Right, and from here to here, the max polling The feature maps have shrunk into 13 by 13 and the number is same. Next convolution, it goes to 384 feature map sizes 13 by 13, 384, 13 by 13, again same size, right? And then 256, 13 by 13, 266 by 6. So actually, there's a reduction in the number of feature maps. Then followed by fully connected layers, each of size about 4,000. And the final stage is 1,000 because you have 1,000 classes. So what they have done in this network, in this architecture, is they have split this architecture into what is called two columns to just split it horizontally or sorry, vertically. And they run different parts of this network on different GPUs just to parallelize it and speed up the computation. Now, one feature that they added is something called local response normalization. So if you have the output of a feature map, there's some kind of a competition that is set up between among the activities of different neurons. Because like I said, one of the objectives of training is to make sure that a minimal number of neurons respond to any given pattern. Every neuron or a large number of neurons responding to all patterns will be a kind of superfluous and a redundant kind of representation. Right. So this kind of minimal response will happen if you have some kind of a competition among neurons. So one way to set up competition is by dividing the activities of all neurons by some kind of a total activity of the entire array. So by some kind of a normalization. So they do that by this method. The activity AXYI is activity of ith kernel at position XY, and divide that by the total activity, which is in terms of squared activity. So this is the kind of normalization that they use, and this normalization is found to decrease the learning rates by about 1.4% or 1.2%. Okay, so like I said, this is split along the kind of length of the network into two. So other people also have used this kind of a multi-column architecture. That is, instead of taking just one CNN, so one pipeline going from input image to the output classification layer, they take multiple parallel pipelines and then combine them at the output by averaging or by taking. There are various ways of combining, right? So think of each network as an expert at classifying these stars, and you basically, if you put a lot of heads together, that's likely to give you better performance. So take multiple CNNs and combine them. But point is, if you give the same image to all CNNs and train all of them in the same way, and then why will they be different? If they are not different, what's the point in combining them? So to answer that question, what they do is they apply some kind of a pre-processing to the image, right? So different kind of pre-processing is applied to the image, and then that pre-processed image is applied to different CNNs. Also, CNNs are made different by a different another means also, which is by different weight initialization. Your initial weights are different, and even if you train the network on the same data set, your final CNN is going to be slightly different, right? So like that, you create some kind of a diversity of CNNs, and they call this columns, and you combine them. So this idea of a column is again inspired by brain, because in the brain you have the surface of the brain is covered by this sheet of cells called the cortex, and so this is a cortex. In the cortex, neurons are generally divided, organized into columns. So where within a column, neurons do about very similar functions. So neighboring columns do different functions, but within a column, they do very similar functions. So this is called a columnar organization in the cortex. Okay, so from that, they use this term multi-column architecture. So here the purpose is to amplify the performance, whereas in this case the purpose is to mainly split it and then put it on different GPUs and speed up training. So this is that these are the two columns. You split it like this. Now for improving generalization or reducing overfitting, both mean the same thing. They use something called a dropover. So for generalization, basically you need to have a minimal network. So the number of, like if you remember what we discussed in the generation discussion, For best generalization, so to achieve best generalization, you need to make sure that the problem complexity is matched by the network complexity. Network complexity means number of free parameters, not number of weights. So, so if you take a very large network for a tiny problem, then it's going to overfit, right? We saw all those examples before. So many ways of for reducing network complexity. These are a huge list of techniques called pruning techniques. So here they use something called they use a more dynamic way of reducing network complexity, and this is done in the on the fly, during the forward pass when the network is taking an input and producing an output. So in the figure you see, in the left figure you see the picture of a standard neural net. So it gives some input to the input layer, and then you get the output Y in the output layer. So you have so many hidden layers and so many weights and so on and so forth. So if you want to reduce this network size effectively, one way to do it is chopping the weights and all that. That is what is done in traditional pruning. In dropout, what they do is when you give an input vector X, you imagine that certain neurons are dysfunctional, they're out of action just for this moment. So when you present that input for that present input presentation, imagine that certain randomly selected neurons are out of action. So they are just shut out, and that is called dropout. So they are dropped out of the computation for that particular input. So only the other neurons. So that means basically the outputs of those neurons is set to 0 for that forward pass. Only the remaining neurons are used, and then you get the output. So this is done randomly with a probability of 0.5. So effectively you are using only like half of the network on any given forward pass. It might seem weird, but it gives great results. It gives very good generalization. So this and this dropout is also implemented during the backward pass also during the back propagation. So in the forward pass, right, you knock off these neurons and you don't use them. You don't participate in the computation. Even during backprop, so when you find the error here and backpropagate it, you don't. You basically use this neuron output to be 0, and accordingly you calculate the weight updates. So dropout was implemented only in the first two of the 4096 fully connected layers, and so without this step, without this dropout procedure, network is found to exhibit a lot of overfitting. But the only thing is because of dropout is like adding noise. The way they're implementing dropout is like adding noise, so therefore it takes longer to converge. But the performance on the test set, which is what generalization is all about, that improves. Then to speed up, they use what is called momentum. So momentum means so basically when an object is moving, right? So if it is, so the thing is, if you have a ball rolling down the valley, right? The force acting on it is proportional to the gradient of this. So call this. Think of this as a potential function, right? It's rolling down a slope, right? So it is doing some kind of a gradient descent. But unlike the gradient descent that we use in neural network models, so where you have delta W is proportional to minus dou F by dou W something, so dou E by dou W, something like that. So in the physics, right, when a ball rolls down a slope like a potential function, as it goes down, it gains velocity, right? Its velocity doesn't depend only on the gradient; it also depends on past history, right? So that is called momentum. That's why you say it gains momentum. Whereas in the way we do gradient descent, there is no such gaining of momentum. So the idea here is if you add a feature to the weight update, where so how if it had already traveled a long stretch of high gradient, part of the error function, it should do it faster, like in the future iterations. So to do that, they have this extra term, right, where minus epsilon times, sorry, this is the weight decay term. So this is the momentum term. So add pass gradient, right, and with a small weightage called epsilon. So okay, so yeah, and because of this, you have faster like update the rates. So with all these features, the proposed network, the CNN architecture gives much better performance. It's a very hard problem, 1,000 classes and very noisy data. So so the error performance is only about 37.5 compared to the previous best methods, right, which gave 45%, 47%, so on. This in itself might seem very high, but for this data set, it's a good output. Compared to, so we are used to seeing performances like 99.6 and 7 and all that, and in case of MNIST data, but this is a much harder data. Okay, so this picture just shows a bunch of kernels from the first hidden layer. Again, so you can see that the first hidden layer kernels very often respond to simple linear patterns, like a ledge with some orientation. And you can also see some of them responding to colored patches. So some respond to monochrome kind of edge features. Some respond to colored patches, which is quite interesting because in the brain, in the visual system, in the what is called the primary visual cortex V1, right? You do find neurons which either respond to edges without any color or respond to colored patches without any sensitivity to edge and its orientation. So you see both kinds of neurons. Interestingly, you find that kind of a organization emerging here automatically. Okay, so and also one of the things that we learned from all these studies is that depth is important. It's good to have a lot of hidden layers, right? And they found that in this study, removing even a single convolutional layer degrades performance. So again, we learn why deep networks are important and why they've created such a revolution, right? Although the approximation theorem says that if we have a large enough hidden layer, a single hidden layer should do. In practice, they don't train that well. So a deep neural network is better. So the examples that we have seen CNN are all from image processing. So let us see an example from speech processing. Because speech recognition also has improved a lot over the last decade, especially if you look at applications, popular applications like Siri or Alexa. It's really quite fascinating how much the speech recognition has progressed. So for the speech recognition, basically you convert a signal into some kind of an image, right? So what the signal varies through time, whereas you convert it into some kind of a spatial structure. So what they do is by applying something called time delays. So I have a signal called discrete signal, let us say, which is xn. Okay, so xn, xn plus 1, and so on and so forth. You convert this, take a window of these discrete samples, right, and then it becomes a vector. So that vector represents a small speech sample, and simultaneously you're not sending samples one after another. You're taking a chunk of these samples and convert it into a vector. Now there is a construct called, I don't know if you have done any filter theory in your first year in your basic electrical engineering course, but there's something called an finite impulse response filter or FIR filter, which is computed like this. If I have a signal like this going from, ideally from minus infinity to some time t, I take a chunk of that signal going from xn to xn minus capital N. So you're taking capital N samples of the signal and multiply that with a bunch of coefficients, b0, b1 up to bn. And this summation gives you the output. So basically think of this as a box, right? And the input to the box is all these samples. So xn up to xn minus n. Okay, and the weights of these inputs are these coefficients b0 to bn. And output of this box is y or yn. Okay, now you can see immediately that this looks like a neuron, right? Because a bunch of input variables, pass through some weights, and then combine, and then all this together produce an output. That looks a lot like a simple artificial neuron. So that is a kind of recognition behind formulating a neuron model, right, as an FIR filter. So since neuron is a nonlinear, implements a nonlinear function, the FIR neuron becomes a nonlinear FIR filter. So here what you do is you take the input signal, x of t, time delay it, right, at various times, and you get xn, xn minus 1, and so on. Pass them to a bunch of weights, add them up, pass the sum through a nonlinear function. Of course, there's also a bias term or a threshold term. Pass it through a nonlinear function, and you get some output. So this is the FIR neuron. So when you construct a convolutional network for signal processing, or for in this case, speech recognition, right? It is made up of this kind of FIR neurons. So let us take this paper, right? This paper estimates, does phoneme classification. Phonemes are the smallest unit of speech, right? Let's say you have a sound like key, right? Key, the sound key is made up of, is a syllable made up of two phonemes, ka and e, right? So that's the smallest unit, intelligible unit of speech, kind of like an atom of speech, and syllables are like molecules of speech. So here also you have convolutional layers and you have max pooling layers, but these pictures are not that easy to understand. I found a much more elegant picture from this another paper by Abdul Hamid Tal. So basically what is happening in this problems is you are converting the input image signal into, input signal into an image, into two-dimensional. Signal is a one-dimensional structure. They convert it into a two-dimensional structure. And once you convert it, then that image is given to a convolutional network, just like what you do in case of an image processing or image recognition. So these guys, so you have, let us say, a signal like this. So some speech signal like this. You divide this into small chunks. Okay, and from each chunk they extract, they do Fourier transform. Okay, so they compute FFT of that, and you get the frequency spectrum over that small chunk of the signal, and that becomes one column of this image. So like that, you keep on moving this window. You can take overlapping windows. As the window gradually keeps moving, the spectrum also keeps changing gradually. Okay, so the spectrum shows up in the y-axis and time is in the x-axis, and you take so much interval, to represent in this image. So you take only some, let us say some, so many frames. Okay, so that is the number of frames on the x-axis. So that's all. Once you have an image representation like this, so after that, it's business as usual. You have convolutional layers, and again, each neuron takes an input from a window in the previous layer, and that window also. So in the x-axis, since it represents time, it takes inputs from samples over multiple, time instants. In the y-axis represents frequency, so it takes inputs from a certain band of frequencies. Okay, so which is very interesting. It is combining the time domain and frequency domain in the same window, and taking that as input and computing response of the neuron. So after that, it is just straightforward. So these kinds of networks are also quite powerful. It's a very simple architecture, but quite powerful for this problem. So the final layer has is a softmax layer, just like generally you use softmax if you are applying it for a classification problem. So dataset used is something called TIMIT acoustic phonetic corpus. It's a standard speech corpus for phoneme data. Training data had about 3,600 utterances, and sampling rate is 16 kilohertz. Data is taken from 462 speakers. The validation data, test data, is described here. The totally 39 phonemes are, so that is 39 classes. Right, network gives about 71%. This itself is considered a pretty good number. But so thing is, this looks pretty low compared to your performance of Alexa or Siri, because when you're looking at the running speech, you also have a lot of top-down information. So you recognize the word level and then give feedback on your estimates of the word that you recognize, and then you can fine-tune your recognition accuracies of at phoneme level and so on. If you look at if you hear a single phoneme, it might be very hard to recognize. Even for us, if you play a single, very brief sound, it's very hard to recognize it. If you play a longer sound, in the context of the longer sound, it is easy to recognize single letters. So that's why when you're conveying, so let's say a password or something like that over a phone, right? You don't say single letters. You say A for apple, B for boy, V for victory, and things like that. That is because single phonemes are easy to misclassify. But if you give it in the context of a longer word, that can be more accurately recognized. So anyway, this is better than some of the traditional techniques. So that's what the paper says. So that completes our discussion of CNNs and deep networks. There's just one more topic I want to cover. This will be the last topic. So I'll introduce the topic and we can stop there. Maybe then I'll cover it in the next class. So this last topic is called principal component analysis. So this is a way of reducing data dimension or data reduction or dimensionality reduction method. Okay, so let us say you take some real world data and you are trying to build classifiers and things like that. So let's say this has 53 parameters from some blood work, and you can show this as a matrix, right? You can simply show, so suppose you have multiple. So this is taken from multiple subjects, right? Now, how do you depict this? So say so in the first plot, which is univariate, the people are on the x-axis, and the y-axis you have first variable, whatever it is, h bands, whatever that means, the first variable, and show it as a graph. And you can see some idea, you can get some idea of how much it is by how much it's varying from person to person, right? Or you do a bivariate depiction where you have a scatter plot, right? Where you can show two parameters simultaneously and you get some idea of the scatter. Or you can do the same thing, a trivariate depiction with three parameters, and already it gets very messy because you cannot understand, you cannot really judge the depth when you just show a bunch of points like this in 3D space, because ultimately it's a 2D depiction. So the point is we have 3D-dimensional space for viewing data. How are you going to view them, right, and get an intuition about the kind of distribution of the data, right? So the intuition behind this whole algorithm is to transform these high-dimensional vectors into a low-dimensional space in such a way that the differences in the higher dimensionals, right, are captured to the best possible extent in the lower dimensions. Or the way it is done is you find out what is the subspace in which there is maximum variation in the data, right, and then you transform this data into that subspace and then try to visualize the data in that subspace. Hopefully, it is a small dimensional space. So this idea of finding out what are the most important dimensions, right? What is a subspace in which there is maximum variation, right? That is called principal component analysis, or PCA. This is possible because for a lot of real data, although the data itself is higher dimensional, most of the you can actually show that the data actually is embedded or confined to only a smaller dimensional subspace. A simple intuitive example is, let's say, our Milky Way galaxy. So galaxy, the stars are distributed in 3D space, in 3D volume, right? So it is, strictly speaking, 3D. But most of the stars can be confined to a two-dimensional plane, right? So there's not much variation, relatively speaking. So I think Milky Way is about 1 lakh light years wide, whereas the height, the vertical variation is not much. So even if I give the coordinates of a given star like sun, simply if I give the x and y coordinates, that might be good enough, right, to locate it in this space. So identifying that in a distribution of data set like this, the third dimension is not very important, and you can capture most of the variation in the first two dimensions. That's an example, right? And that's how you find out the scope for dimensionality reduction. So what you do in dimensionality reduction is you have an input vector x of dimension n. You want to reduce it to another vector of dimension m, where m is less than n, in such a way that it should be possible to transform y back to x, and we call that x hat, right, which is the reconstructed vector, and which is also obviously of dimension n, which is same as input dimension. And the idea is you should be able to reconstruct in such a way that x hat is as close as possible to x. So is this first of all possible? Because x is n, and let's say x is 100-dimensional, and I'll somehow use a weight matrix and convert this into 10 dimensions, which is a much smaller number. And from this 10-dimensional vector, again, I use another weight matrix, okay, some w prime, right, and convert this back to 100 dimensions. And I somehow, like magic, the reconstructed x hats will be approximately equal to x, right? If I can achieve that, then I'm able to achieve this kind of a dimensionality reduction. So how do we do that? So I'll present a very simple method based on neural networks in this class. Then we'll continue this in the next class. The simplest method, which we can easily understand with all the background that we have gained so far, is what is called an autoencoder. So if you look at this picture, this picture almost looks like a neural network, an MLP with a single hidden layer, right? So I can think of an MLP which has an input layer of dimensionality n and a hidden layer of dimensionality m, and an output layer again of dimensionality n. So I have weights going from here to here. So these are W n by m weights, and weights going from here to here. These are weights W m by n weights. Okay, and then I have x hat as output and x as input. So the network is trying to reproduce the input x in its output. Okay, which means how do you train this? It doesn't make any sense, right? So how do you train this? You use x as a desired output. So d here is equal to x. Now d is defined to be equal to x, right? So you're trying to train the network so that you map the input onto itself. So then if it succeeds in reproducing x, that is x hat is right approximately close to x, then in principle you have achieved this dimensionality reduction. So point is what you will typically see is, suppose m is equal to n, then it's trivial. In fact, if m is equal to n, I can just have straight lines, direct connections from neuron to neuron, from input to hidden to output, right? I can just use a kind of a identity matrix, right? If n is equal to m, w is identity matrix, this also is an identity matrix, right? And it's a trivial problem. But from that, so let me plot this. So error as a function of m, and this is the maximum, because there's no point going beyond that. I mean, we want to reduce m and make it less than n, so we won't be even considering values greater than n. So for m equal to n, you expect zero error. So as m goes down, right, you expect error to go up rather, right? And for m equal to 1, it will be really high. Okay, so what happens is, so you can think of it as maybe varying like this. That is one possibility. Or you can think of it as varying like this. That is not only at m equal to n, even for much smaller n, maybe error will be very low or almost zero. Only if you decrease m beyond a point, error will start going up. This is one possibility. So what happens is, for a lot of real world data, this will be the case. That is, you can manage with an m which is much smaller than the input. And only when you reduce it too much, you'll see error going up. Right. So this nature of the input data, real world data, like this example of this galaxy, right, is what gives you scope for dimension detection. So there's an algorithm for doing this. This is, I mean, the neural network is a nonlinear model. There's a linear analysis that you do to find out how this is done. So what we'll do, we'll describe that in the next class, or maybe I'll introduce that quickly and we can continue in the next class.